Hey everybody, today we're getting started with curve sketching. Here I've got a problem where I'm given some information about a function and its first two derivatives, and I'm asked to come up with a rough sketch of what the graph might look like. So as I tackle a problem like this, I always want to bear in mind that the derivative is telling me where a function is increasing and decreasing, and the second derivative is telling me where it's concave up and where it's concave down. I have some axes ready to go. I'm going to start with any points that they give me. So here, they're just telling us that f of 0 is 0. So I have exactly one point on the graph that I know the graph is going to pass through the origin. Now I'm moving on to the first derivative. I know I'm going to have horizontal tangents at 0 and 3. In particular, at 0, I have a horizontal tangent. I'll draw a little bit of a horizontal tick right there. And I know that the first derivative is going to be negative between negative infinity and 0 and also 0 and 3. Let's just make a note of that below the axes. From negative infinity to 0, the first derivative is negative, so the function is going to be decreasing. And then again, from 0 to 3, the function is going to be decreasing. Then the function's first derivative changes to positive from 3 to infinity, so the function becomes increasing. Great. So the function is going to go down, down, and then up. Let's move on to the second derivative. Between negative infinity and 0, the second derivative is positive, so the graph is going to be concave up. Again, I'll make a note below the axes. The graph is concave up. And then again, from 2 to infinity, 2 to infinity, concave up. In between, it's concave down. Okay, so as I look at this, I see that there are basically 4 different spots I have to think about, 4 different kinds of intervals. 1, 2, 3, and 4. The behavior of the function generally can change at 0, 2, and 3. And then after 3, it stays the same forever. Okay, decreasing, concave up. So I know concave up is like the bottom of a valley, so I want the decreasing part of a valley. It's going to look like that. Then decreasing, concave down. Concave down is like the top of a hill. I want the decreasing part of the hill. It's going to look like this. Here, I'm still decreasing, but now concave up, like this. And then increasing and concave up is like this. When I'm thinking about combinations of increasing, decreasing, concave up, and concave down, I always think in terms of that unit circle. In each of those 4 quadrants, you get each of the 4 behaviors. And so you can sort of go around the unit circle until you get to the right one. All right. Now I know roughly what my graph is going to look like on each of these 4 intervals. I just need to piece them together. I have to pass through the point 0, 0, and I need to have a horizontal tangent there. Also, let's bear in mind that one other piece of information I haven't used yet, which is that f prime of 3 is 0. I need a horizontal tangent there. So here, I'm going to take this general shape and translate it up here. Let me just redraw that so that it actually goes through the origin a bit. A bit more like that. I can believe that has a horizontal tangent there. Now decreasing concave down until I get to 2. Decreasing concave down. Decreasing concave up until I get to 3, where I need a horizontal tangent. So like that. Local minimum here, as you can see, I've got a first derivative that's 0. The function's going from decreasing to increasing. And then from then on, the function's going to be increasing, concave up. Overall, this is what our graph looks like. Let's complete this picture by explicitly labeling our local extrema and points of inflection. So as I mentioned, here at x equals 3, we have a local min. By the first derivative test, we would know that even if we didn't have the picture, because we see that the function changes from decreasing to increasing. The first derivative goes from negative to positive at x equals 3. We have 2 points of inflection here, at x equals 0 and x equals 2. Those are points of inflection. At x equals 0, the second derivative changes from positive to negative, and at x equals 2, it changes from negative to positive. Those are both points of inflection. Overall, this is a pretty good sketch of what the graph of a function with these properties must look like.